Today we're going to do Chapter 6, Quantitative Relationships in Chemistry. Basically what we're doing in this chapter is stoichiometry. We're going to take the art of balancing equations that we developed before break, and we're going to use the coefficients to define the yields in reaction. Theoretical yield, followed by actual yield and percentage yield. So let's go ahead and back up a little bit. We have talked a lot about chemical reactions now. Going from reactants to products, connected by a reaction arrow, which we said had the properties of an equal sign. Same numbers and types of atoms on both sides. Now, in order to ensure that, we insert numeric coefficients, usually integers, and the coefficients define the stoichiometry of the reaction. This reaction, as it sits, we all recognize as unbalanced. We have an even number of bromines here, odd number this side. We can fix that by doubling this. That gives us 6 bromines, so we need 3 Br2s. And finally 2 aluminums. We now have 2 aluminums, 6 bromine atoms on each side. So we're balanced. Now the stoichiometry that we have just done here also defines what we will call the theoretical yield for the reaction. Basically, if we take 2 moles of bromine, of aluminum, 3 moles of bromine, we will get 2 moles of aluminum bromide. Now in this particular reaction, if we remember, bromine is a liquid at room temperature. As it reacts, it forms huge clouds of gas and they bubble away. In a case like that, we use what's called excess bromine. We still have the same stoichiometry for aluminum, and that will define the theoretical yield. But we have all the bromine that we could possibly need. Simple concept. Any questions? Well, let's go ahead and look at a real problem then. Here we have the organic alcohol ethanol reacting with oxygen. Remember, oxygen, molecular oxygen is O2, to give CO2 and water. In this problem, we're looking to see how many moles of carbon dioxide we're going to get, just this, if we have 2.5 moles of ethanol. So that's defined as our problem. Oxygen is in excess because this is burning in the room, full of oxygen. According to this equation and this balance, 1 mole of ethanol gives 2 moles of CO2. So a ratio of 1 to 2. We look at our problem here. Our given is 2.5 moles of ethanol. So when we write our ratio, we put this in the denominator, moles of ethanol, the unit. And our given, like I said, is 2.5 moles. So we have a setup that looks like this. 2.5 moles of ethanol, here's our ratio. Again, units match. And we're trying to find CO2. Start off with our given. Multiplied by our ratio. Moles of ethanol cancel nicely. And we should get only moles of CO2. 2.5 times 2 divided by 1 is 5. I can do that without even a calculator. Any questions? Well, this method works very nicely, okay? It's our given ratio find method. There's a simpler method though, one that's basically the same math, except it's a little more compact and somewhat easier to do on your calculator. So let's look at it that way. This one uses two ratios, not just one. The known ratio from the stoichiometry and an unknown ratio from the problem. For our known ratio, we looked at the balance equation. Ratio between ethanol and CO2. Ethanols are given, so there's going to be in our denominator. It's going to be simply that. That's our known ratio. The unknown ratio, you go and you look at the problem. You're going to do the find over the given. What we're trying to find here is moles of CO2. We're going to call that X. Moles of ethanol are given, so let's stick both of those in. There it is. Now, as you just look at these two ratios, it's very intuitive to see you can just cross multiply. 2.5 times 2 divided by 1. Whip through it on your calculator, no problem. Moles of ethanol, cancel nicely. 2.5 times 2 divided by 1. Makes it a little bit simpler, a little more direct. If we instead wrote it out, take our unknown ratio here, move this up. This is find, given, and ratio. So it's the same method, it's just a little more compact. Don't have to write things twice. Any questions? Once again, if we did it this way, these will cancel, and we're left with 5 moles of CO2. So this is stoichiometry, and this is how you really use stoichiometry. So let's do a bunch more problems. Calcium reacts with HCl. We've done this in lab. The chemical equation is here. It looks like it's balanced to me. We want to know how many moles of HCl we need to react with 3.25 moles of calcium. So, what we're looking at is the relationship between HCl and calcium. They're both reactants, but that works fine. And it's 2 HCl's for every calcium. Calcium will be our given, so our ratio is going to have calcium in the denominator. Our ratio would look like this. 2 moles of HCl for every 1 mole of calcium. We are trying to find moles of HCl, so let's put that as our X in our equation. Our given is going to be 3.25 moles of calcium. So the known ratio would look like this. Again, the math is fairly simple. You don't have to rewrite anything. 3.25 times 2 divided by 1. Moles of calcium cancel nicely. Do the math. If we did it out the long way, moles of calcium still cancel, and we get 6.5 moles of HCl. Any questions? Let's do another one. Now, unlike everything else at this lecture, this guy is not balanced. We did that in chapter 5. So let's go ahead and think about balancing it. First thing I notice is we have 2 carbons here, 1 on this side. We can fix that with the 2. Now, carbons balanced. We have 6 hydrogens, only 2, so we need a 3 here. Now the oxygens. We have 1, 2, 3, 4, 5, 6, 7. But remember, oxygen comes in pairs, doesn't it? O2. So that would be 3.5. This is a legally balanced equation. Yes, it is. Okay? Pushing the limit, this is legally balanced. But we really like to have integer coefficients. So whenever you have something like this, where you have 3.5, 6.5, whatever, first thing to do is just try doubling everything. Instead of 1 ethane, we would have 2, 7 oxygen, 4 CO2s, and 6 waters. Yep, that works. Now, we are looking at molecular oxygen. Whenever I say molecular oxygen, we're talking O2. And carbon dioxide. It's 7 to 4. CO2 is going to be our given, so this is in our denominator. We're going to write it like that. 7 oxygens, 4 CO2s. Now the unknown ratio, we're looking for moles of molecular oxygen, that's our X. Our given, as we said, 1.7 moles of CO2. So the unknown ratio looks like that. The math is simple. 1.7 times 7 divided by 4. Moles of CO2 cancel. If you wrote it out the long way, you would do this. And again, the math is very simple. 2.975 moles of oxygen. Now, we are dealing with 3 significant figures, right? This is 4. We round this to 9/8, we're down to 9/7. There's a rule for that, remember. The rule is round even. So this goes to 9/8. Any questions? Here's another one. We have molecular oxygen reacting with fluoroacetic acid to give carbon monoxide, water, and HCl. We want to know how many moles of oxygen, 4.2645 to give 0.2645 moles of CO. All right, CO is going to be our given. So that's going to be in our denominator. 1 mole of oxygen, 4 moles of CO. Our known ratio looks like that. Okay, that's the known ratio, no problem. Unknown ratio of moles of oxygen is our unknown. This is our given. That's the unknown ratio. Simply cross multiply. 0.2645 times 1 divided by 4. Moles of CO cancel. And we're left with this. Now again, there's lots of digits here. We have 4 significant figures. 66125 is what my calculator gave me. We need to round this to 4. What's it round to? Well, in this case, it's going to go even again, but we're rounding down this time. Statistically, you round up and down the same amount. Any questions? All right, this is the first tutorial. This one is really nice and really simple because it gives you the unknown ratio right here. No problem. What you're trying to find over the given. We are looking at the relationship between sodium hydrogen carbonate and sodium carbonate. We have 2 sodium hydrogen carbonates for every 1 sodium carbonate. Our given is sodium carbonate, so it's going to be a 2-to-1 ratio. Hydrogen carbonate over carbonate, 2-to-1. That's our unknown ratio from here. That's our known ratio from the stoichiometry. Simply multiply 0.82 times 2 divided by 1, and we get 1.643 moles. Any questions? Let's do one more because these are easy. Again, find over given. That's the unknown ratio. Our given is going to be chlorine, and we're looking at fluoroethane. So here's fluoroethane, here's chlorine. It's a 4-to-2 or 2-to-1, either one. Either way you want to write it. This is also a very interesting equation to look at. I gave that once on an exam when I was feeling particularly angry one day. I don't do that anymore because I'm so at peace. But, yeah, this is quite an equation to balance. You wind up from the first pass with 6.5 water or oxygen, and then you double everything. So, all right. Our ratio is 2-to-1. From this, we get our unknown ratio. The math is 0.99 times 2 divided by 1, and we get 1.983. Any questions? Well, this isn't so bad, is it? Stoichiometry is supposed to be scary. It's not. Can be. Let's move on just a little bit. Remember the gummy bear reaction. We took potassium chlorate, heated it, got potassium chloride and oxygen. In this problem, we're facing something real that you would do in the lab, okay? In the lab, you don't weigh out moles of things, you weigh out grams of things, don't you? So here we want to know how many grams of this stuff we need to get 2.25 moles of oxygen. Now, there are a couple ways to do this. The simplest, I think, is to simply solve it the way we've been solving everything else. That is, do the entire problem in terms of moles. Once you've done it in terms of moles, and you know how many moles of potassium chlorate, then convert that to grams. So let's do that. 2 moles of potassium chlorate, 6 moles of oxygen atoms. Now I've done this deliberately, made this in terms of oxygen atoms, in terms of oxygen, just to point out if I want to know O's, not O2's, I use the term oxygen atoms. So, okay, we have 2 to 6. Oxygen is going to be our given, so that's going to be in our denominator. 2 moles of potassium chlorate, 6 moles of oxygen atoms. The unknown, grams of potassium chlorate, moles of oxygen atoms. The math is simple. 2.25 times 2 divided by 6. Moles of oxygen atoms cancel. And we get 0.75 moles of potassium chlorate.
How we would round for even number? Like if it's 0.750. Like is the 0 considered as a like even?
No, we're not rounding anything yet. Don't round or you're all done. So, this is how many moles we need. From the last exam, we all remember closely how to convert moles into grams. We can do that because we know mass over molar mass is moles, and therefore, since we're looking for mass, it's simply molar mass times moles. So we'll take our moles, that's 0.75. We need to multiply that by the molar mass here. Have to add it up. Turns out to be about 122.5. So 122.5 times 0.75. Moles cancel. And we're left with 91.9 grams. So, once again in this problem, one of the things we were interested in was in terms of grams. Far more common for a lab experiment is if everything is in terms of mass. Then we're taking zinc sulfide, reacting it with oxygen to get zinc oxide and sulfur dioxide. We want to know how many grams of zinc oxide we're going to get from 25 grams of zinc sulfide. So it's a real problem. You're going to weigh out 25 grams of this stuff, and you want to know how much of this you're going to get. To do this, we're going to use what we will call a mass ratio. Our equation, 1 zinc sulfide, 1 zinc oxide. 1 to 1, 2 to 2, same thing. Here I have zinc sulfide, here I have zinc oxide. Our unknown ratio, we're looking for how many grams. Oh, wait, we need to make this into grams, don't we? I forgot. These are the molar masses for each of them. Instead of writing it simply zinc sulfide over zinc oxide, we could simply substitute the molar masses for each. So this ratio is identical to that one. That's it in terms of moles, and that's it in terms of mass. Okay, now trying to find zinc oxide. That's our X. We have a given of grams of zinc sulfide. That defines our unknown ratio. Oh, shoot. I did it upside down, didn't I? I should have noted zinc sulfide was going to be our given and put that in the denominator. But if you ever do this, what's our solution? We simply turn them both over. Totally legal, as long as you do both sides. Okay, now it's easier. Going to be 25 times 81 divided by 97. Zinc sulfide will cancel. And we're left with 20.9 grams of zinc oxide. So we start with 25 grams here, release sulfur dioxide, and we get about 21 grams of zinc oxide. Once again, these are all the theoretical yields, okay? We are calculating how much we're going to get if everything works perfectly. Let's elaborate a little bit on the mass ratio. We're going to define a mass ratio as simply the coefficient multiplied by the molar mass. Here we're looking at grams of water, grams of HF. Grams of water, grams of HF. It's a 1 to 2 ratio, isn't it? Grams of HF is going to be our given, and that's in our denominator. So we have our mole ratios look something like this. 2 moles of water, 4 moles of HF. Now to get this into a mass ratio, we're simply going to multiply the coefficient, 2 and 4, by the molar masses. They're given 18 and 20. So 2 waters at 18 each, 4 HFs at 20 each. Simply multiply these out. Lots of stuff cancels. And we get this odd set of numbers. Not really an odd set though. It can make it nice and intuitive. What this tells us is that for every 80 grams of HF, we need 36 grams of water. Okay, that's a mass ratio. Now, our unknown ratio. How many grams of water? That's unknown. 64 grams is the given. 64 times 36 divided by 80, about 28 grams of water. Any questions? All right, the next tutorial looks like this. This isn't quite as straightforward and obvious as the other one. And we're going to need to use a mass ratio because these are all in terms of mass. Here we have cobalt-2 reacting with oxygen to give cobalt-3. It's a redox reaction, isn't it? The cobalt is being oxidized because it's losing an electron. So, let's see. we have a ratio here of 4 to 2, or 2 to 1. Our given is going to be cobalt 3, so that's going to be in our denominator. 4 moles of cobalt 2, 2 moles of cobalt 3. Write the mole ratio and a mass ratio and work from there. So, to get our mass ratio, we start with the stoichiometric ratio, 4 to 2. We are given molar masses, so this will be 4 times 74.9, 2 times 166. Now we could do what we did in the last slide, but on this one I didn't, just to show the versatility here. This is a ratio, isn't it? This is given, isn't it? We can just take this whole ugly ratio, multiply it by the given, and get our result. Here's our given, here's our big ugly ratio. Again, on the calculator, 41 times 4 times 75 divided by 2 divided by 166. Do all of those magic numbers, cancel a lot, and you get about 37 grams of cobalt 2. So there are lots of ways you can do this, just whatever works for you, whatever is simple and straightforward. Any questions? All right. The next topic is called limiting reactants. In limiting reactants, in order to do the problem quantitatively, you're going to do the same thing we've been doing over and over again, except you do it twice. In 110, I don't do limiting reactions and calculations because, well, doing it once is bad enough. Doing it twice, you have lots of chances for errors. General chemistry loves limiting reactant problems. We can do it then. All right? But for now, the concept here, we're reacting A and B together. We have a given amount of A and a given amount of B, not excess, given set amounts. The smaller molar amount is called the limiting reactant, and it defines the theoretical yield. Unless the two molar amounts are exactly the same, the other one is called the excess reactant, and you have leftovers. So spring is coming. You wouldn't know it this morning, but think of gloves. We all wore gloves when it was really cold. And we've got a big stack in the closet, right? We have 4 lefts and 3 rights. Which set of the gloves is limited? Well, you take your stack, grab a left and a right, grab another left and right, and another, and we're left with a right-handed glove left over. We have 3 pairs and a leftover. That's all limiting reactants are. Now on an exam, I'm not going to ask you about gloves. I'm not going to ask you to do all of the calculations twice. But I will ask you an intuitive question. Okay? Here's an example of an intuitive question. If you take fluorine and chlorine reactive, you can make fluorine trifluoride. This works because fluorine is a third period element. We can put lots of electrons around it. So, in this reaction, 3 fluorines react with 1 fluorine. They're both diatomic. An intuitive approach to this would be to show something like this, either as a cartoon or just in words. So here we have 1, 2, 3, 4, 5, 6 fluorines and 3 fluorines. Questions might be who's limiting, who's in excess. So, if we look at our equation here, 2 atoms of fluorine, that's a Cl2, requires 6 atoms of fluorine, that's a 3 F2s. So let's look at our little cartoon. Let's grab 3 fluorines and 1 fluorine. We will make 2 ClF3s. Let's do that again. 3 fluorines, 1 fluorine, 2 more. Now we're out of fluorine, aren't we? We have fluorine left over. That's the excess reagent. Fluorine was limited. So it's a simple concept. One limits the theoretical yield, the other one is leftovers. Any questions? All right, well, let's go and talk a little bit more about the concept of a yield. We said that the balanced equation gives a stoichiometry that defines the theoretical yield. For this guy again, 2 moles, 3 moles, 2 moles. If we had excess bromine or even excess aluminum, then the coefficient here would define the yield. Two, 3 moles of bromine, excess aluminum, 2 moles of aluminum bromide. So, theoretical yield, we would say, would be 2 moles. That's simple. In lab, you calculate yield every time you do a real reaction to see how good you're doing. Now, a chemical reaction doesn't just magically jump from reactants to products. The process of the reaction is basically described by a potential energy surface. You have a bunch of reactants here, and they're all at different energy levels. They go over the lowest bump here, activation energy is called, to give products at an energy minimum. There are also other pathways that these guys can take. Think about a mountain range. If we started off here and we had to get over here, I would go down the middle of the valley. Okay? Because that's just what I do. But I'm sure there is somebody in the class that would look at that and say, I'm not going that way. I'm going up here. Takes more energy, but some molecules will do funny things. So, this doesn't form the same product that we get here, does it? Those are called parallel pathways. Percent yield. When you do a reaction, the amount of product you get is called the yield. Theoretical yield is what you expect from the stoichiometry. The actual yield is what you wind up with on the balance. The percentage yield is simply Actual divided by theoretical times 100. Think of popcorn. There are 20 kernels of popcorn here. Our theoretical yield is 20 little puffy balls of popcorn, right? So let's take it, plop it into a pot, and let it pop. Dump it out. And what do we get? If you count, there are 16 that have popped, and we have 4 that did not. The theoretical yield is 20. The actual yield is 16. Percentage yield, 16 over 20 times 100, 80%. Any questions? All right. Let's do a couple examples here. This one is fairly straightforward because you don't have to do any calculations, really. 5 moles of sulfur are expected to yield 1.7 moles of aluminum sulfide by this reaction. When we do it, we weigh the amount of product, convert it to moles, and it's only a mole and a half. What is the percentage yield? Well, theoretical yield was 1.7, actual was 1.5. Actual divided by theoretical times 100. This went in 88%. Let's do another. This one you have to do a little more work. We're taking 10 grams of NO. We're going to react it with oxygen, and we form nitrogen dioxide. We weigh out the nitrogen dioxide, and it's 9.7 grams. So we took 10 grams here, got 9.7 of our product. But we need to convert these into mole quantities, right? Because they're different molecules. Can't just do this divided by that. Doesn't work. 1 mole of NO should yield 1 mole of NO2. We're going to convert the gram quantities to moles and calculate the yield. Mass over molar mass is moles, just to remind ourselves. We have a mass, we need molar masses. There they are. About 30 and about 46. So, for NO, 10 grams divided by molar mass will give us the number of moles. So we should get 0.33 moles of NO2. The actual yield, we have 9.7 grams divided by 46. Do the math, 0.21 moles of NO2. So we expected 0.33, that's the theoretical. We got 0.21. .33, theoretical 0.21. To calculate percent yield, actual divided by theoretical times 100. .63%. One of the things you do when you're a synthetic chemist is you will do a reaction you'll calculate your yield, and then you'll try modifying the reaction conditions to see if you can optimize the yield. In industry, this is a very important process because you don't want to waste the stuff, do you? So you want the product you want. The drug industry, you need to get as high a yield as you possibly can. Now there is a tutorial called percentage yield. I never converted this one to Blackboard because it's just a little confusing sometimes. So you can do this one just for fun on the website, but there's not a Blackboard equivalent. But let's just look and see how it works. Then we're taking trifluoroethane, reacting it with oxygen gas to get carbon monoxide and hydrogen fluoride. We have 15.6 grams of this. We get 6.6 grams of CO. What's the percent yield? Well, 1 mole of trifluoroethane, 2 moles of CO. Let's write a mass ratio. We have mass and we have molar mass, so we can do that. We're going to put trifluoroethane in the denominator and calculate our theoretical yield of CO. 2 COs for every 1 trifluoroethane. Here's the molar masses. For every 84 grams of trifluoroethane, you expect 56 grams of CO. Okay. Our given here, 6.6 grams of CO. Oh, I'm sorry. That was our yield. 15 grams of trifluoroethane is our given. Simply cancel those guys. 15 times 56 divided by 84. 10 grams is what we expect. That's our theoretical yield. Now, actual yield was 6.6. Theoretical 10, actual 6.6. Percentage, actual divided by theoretical, times 100. This went at about 64%. Any questions? Well, this was a nice short chapter for sounding so ominous. We have the following tutorials. Chemical stoichiometry is called for the first one. The second one is mass ratios. Now, this has been a long week, right? Let's just remember. We're doing tutorials now because everybody is in the hunt for 350 total points. This includes all the extra credit. If you hit 350 after taking exam 2, now you must take exam 2, even if you have 400 points. Still have to take it. You get an A in the class and no final. Also, if you remember back before the break, we tried to do Lab 6. Well, we're going to try again. Okay, they took off early. They are now going to prep Lab 6, we hope. Last Wednesday, was it last Wednesday? Wednesday before, whenever. I did a Chapter 6 quiz online for 10 points. If they do manage to prep Lab 6, this 10-point count as extra credits. If they don't, then I don't know what we're gonna do. We'll fake it and do lab 7 or something, okay? And right now, this means that the syllabus and Blackboard is all out of sync. Let's just wait until we do the lab 6 before I try to fix it. Any questions? All right, do your tutorials, 25 points sitting there.